Okay, our last lecture, we talked about last two lectures, human cultural evolution, evolution meaning slow change. And now on the fifth lecture, we're going to talk about particular aspects of the last lecture, was on the basically industrial revolution. So I'm going to talk about the concept of peak oil, the concept of energy return on investment, which is my own
Oh,
personal scientific claim to fame, and the limits to growth, which is very, very different from what we normally see in everyday political and news and so forth life. Um, okay, now let's talk about non-renewable resources. Now, first of all, here's a picture of me doing my PhD work back in 1968 or so, and I'm measuring the movement of fish up the stream. And this is in very low water. The stream is, a fair-sized stream, New Hope Creek in North Carolina. And I would block off, you can see over here on the side, I'd block off at an angle the stream, and all the fish going downstream would get caught in this trap, and all the fish going upstream would be caught in a similar trap that you can't see because it's out of the picture. And there's a cone in the front of this trap that would fit into a cone that was in the barrier, so I could easily lift it out and count the fish inside there. And the first, at that, wait a minute, at that time, the sense in stream biology is, and I call myself a stream biologist, the concept in stream biology at that time was that fish would maintain home rangers and they didn't move. But the very first time I put this trap into New Hope Creek, I caught about 50 fish moving, and pretty fair-sized fish too, a pound or two, some of them. And I said, I've got a thesis here. And over the next 2.5 years, I studied this every day, went out every day and looked at how many fish moved and found that there were lots and lots of fish that were moving in New Hope Creek. Now, at that time, I was strictly interested in ecology of nature, but one fateful day I was browsing the University of North Carolina bookstore and found this book called Resources in Man. That was back in the pre-politically correct Resources and People. But anyway, and I found this book, which was very interesting to me. And it had an article by this guy that I didn't know about previous to that. And his name was M. King Hubbert, Marion King Hubbert, who worked for Shell Oil and sometimes Columbia University and sometimes other things. And I got to actually know him. I once spent about 8 hours with him. And I thought, he might be America's greatest scientist and nobody's ever heard of him. So we're going to talk a bit about him. And he came up with a concept of peak oil. And prior to Hubbert, people thought that when, if there ever was an end to oil, that you would just come to the end of it. But he said no. And I'm going to get to Hubbert's idea, but here is a slide that gives you an idea of depletion. The glass starts full and ends empty. The quicker you drink it, the sooner it is gone. The same principle applies to oil and gas. How has this self-evident reality been concealed? It is obvious, yet it is devastating reality. And this is the guy who wrote that, Colin Campbell. Not a very clear picture of him, but he thought with Guinness Stout, he would show you the concept of peak oil, that there's only so much oil in the ground and you use it and eventually it's going to be gone. Well, the faster you drink it, the sooner it'll be gone.
Right.
Everything we do in society is to use the oil as fast as we can. I suppose we could say we should be happy for shutting down the Straits of Hormuz because it'll save oil for later generations of people, or maybe even later years of people who are alive now. So this is what is called Hubbert's principle. This is the epoch of fossil fuel exploitation. In view of historical things. So 5,000 years ago, Stonehenge was built. Iron in the Middle East was 3,500, Parthenon 3,500, pyramids 2,000, Mayan, and you could see Inquisition, Black Death, and there's the invention of the steam engine. And this will be the use of all fossil fuels, with zero at that time being about 1970. So we're somewhere past that zero on the graph. And then it'll be gone. And we have an entire civilization that's based on fossil fuels. This is everything: oil, gas, coal, oil sands, fracked oil, and so forth. Now, this was Hubbert's original analysis of crude oil production in the United States, and he published it back in 1955. In 1950, right there, where the line goes off the chart, and then this is, he said, exclusive of Alaska. And he said, well, at about half the use of a resource, you'll reach a peak. And this is his idea of peak. It's not you just use it and then it stops. You'll reach a peak and then it'll slowly go down. Now, this was his prediction made in 1955. And he made that prediction a little bit later for oil in the world. And he said sometime, depending on the Q infinity, means the quantity infinite, the final quantity of barrels of oil. And the larger number is more nearly correct. And he predicted a peak. And in fact, there was a peak in conventional oil in 2005. We're not quite aware of it and I'll tell you why. And this is the rate of production of oil. You notice that the rate, this is empirical, what it is for world crude oil. It used to increase very, very rapidly, and then less rapidly. Then came the 1970s, and then slowed down, but a steady rate for a long time at well, you can see down to 1.5 per 1.3%, and then down to 0.1%. So eventually, conventional oil for the world stopped growing about 2005. And that's still true today. Now, remember, that's conventional oil. And he had said 2000s, actually a few years later than that, but not much. Now, this is Hubbert's original graph for the United States, showing a peak sometime around 1970. Whoop, I'm going backwards. I apologize. I was going backwards. Okay, so meanwhile, this was back there in 1980 when we had peak oil. our production was increasing, and the United States used to, in the year 2000, import half of its oil, but it doesn't import half of its oil now. We produce about as much oil as we use, which is about 20 million barrels a day. Now, when Hubbard came up with this idea, the economists did not like this at all. They thought any resource scarcity would be compensated by lower use, and by technology, and by substitution. I don't know exactly what you substitute for oil, except maybe gas. And so this started a big argument, of which I was a small part of, whether the economists were right, or the geologists were correct. And quite curiously, well, let's take a look. Here is the red is the empirical figure. I don't know. And the yellow is it was the production estimate by Hubbard only for the lower 48. And then the green is what was the actual production for the United States. So you see that Hubbard's model was really quite accurate. You could say the yellow and the green, well, they're kind of different. Yeah, but the pattern is certainly very similar. 1980, they're practically almost exactly right. But this was the oil production in the United States up to 2007. And I belonged to a group that was called ASPO, the Association for the Study of Peak Oil. And we were very concerned that American oil production was declining like that. And if you added in Alaska, which was the largest oil field, Prudhoe Bay, ever found in the United States, it added quite a bit. But nevertheless, we went down to half the oil production that we used to have, and we were importing half of our oil. And here's Prudhoe Bay. It was true for Alaska too. It had its own Hubbard curve, a little bit differently shaped, but the same basic idea for the largest oil field we ever had at Prudhoe Bay. And then something happened, and it was this guy, George Mitchell, and his daughter was sipping a milkshake. This is, I'm sorry, not a milkshake. I couldn't find the right picture with a milkshake, but she was sipping through one of these angled straws. And the story goes that she turned her straw upside down to get the last oil out of the milkshake. And this gave George Mitchell the idea that, quite frankly, has saved the ass of the United States politically at this moment, although with some environmental costs for sure, some large costs. And she gave him the idea of horizontal drilling. At least that's the story. So let's go back to, if you remember from last time, how an oil field, a traditional oil field, that oil is generated in spots, in patchy spots in the earth, and migrates up through the strata because it's lighter than rocks, and it's lighter than sand, and it's lighter than water. And it goes into what's happening here? It goes, it's trapped until it hits a trap, which could be an impermeable rock or salt or something else. And then it's trapped. And this is where we got all of our oil into 2007. from a trap, and oil floats on water and gas is above the oil. And if you put your oil well down at the right place in the oil, the gas will push, which is often highly pressured, will push the oil. And that's the idea of the gusher you see or used to see when you drill an oil well. And now they pump it out very carefully. Now you have to have this critical temperature of around 100 degrees Celsius to generate oil. Otherwise, you overcook it, and not enough, you undercook it. Now, this is what it's like. The oil is formed in some source rock, and it goes up. It migrates upwards towards the atmosphere, and some people think that 99% of all the oil that's ever been formed has just gone out into the atmosphere. Remember, these are old marine organisms, microorganisms that have been pressure cooked for 100 million years, and they go into a trap. Well, the idea of fracking is you go down about 2 miles and turn sideways and go through the source rocks. And the oil is not as thick in the source rocks, but you have to frack it. And what you do is you take enormous pumps and pump high pressure water down in the cracks, and then you shoot in very specialized sand that holds the cracks open, and then the oil comes out of the rocks where it's just in these horizontal layers with very low concentrations of oil, then are collected and pumped up to the surface. And this is what is producing 80 to 90% of the oil and gas in the United States now, is this process generated by George Mitchell. The conventional oil is basically almost gone. Now, there are many basins in the United States where this operates. And so the first thing you might think is, oh, there's a huge amount of oil and gas that's available from this approach. And the answer is, well, not quite. Now, there's a lot of gas here, especially in Pennsylvania and New York, although it's not allowed to be mined in New York. Mostly the most active areas now are especially the Permian Basin you see here, the Barnett, Woodford, a little bit from the Niobrara, and quite a bit from Williston, or Bakken it's called as well. That's in Wyoming and especially North Dakota. Most of the rest of these, the procedure doesn't work. Now, this was a map in 2010. This is only the first 2 years of drilling wells in the Bakken formation. And you can see from, you got oil in the green ones and gas in the yellow ones, or mostly gas in the yellow ones. But that although and the size of the circles is the size of the field, how much you got out of it. And you notice that most of them are in this spot, in this partial field, this area. It's called a sweet spot. The sweet spots are where you get a lot of oil and a lot of gas from what you're dealing with. And most of the rest of the big formation, you only get a very small amount. They say it's from 0 to 100 barrels a day in the small circles, and greater than 500 in the large circles. So a very important issue is whether you're drilling in the sweet spots or not. Now, this is what those areas look like. The oil is very diffuse, and you can look from horizon to horizon, and every half mile in grids, there'll be a oil well or a gas well, depending on what you're doing. And And there are huge areas of the United States that now look like this. And here's a way of looking at the lateral extensions are 1 to 2 miles long. So this is in North Dakota, just north of the Missouri River. And this is how dense the wells are. As I said, every half mile or so. And they have 2 mile extensions. So they basically frack a huge area and produce a lot of oil. So now, back in 1980, back in 2008, we reached low from conventional oil. And the unconventional oil now has doubled or trebled the oil production in the United States. So we'd be way below 5,000 now if it were only by conventional oil. But with the fracked oil, we now produce about 12,000. It's a little higher than what's on here. COVID brought the oil down. That's the big dip that you see there. But let's return to pre-fracking. I already had some experience with this. I wrote this article you see in 1981. This is by Hall and Cleveland. And we looked at yield per effort and net energy analysis. And we found a couple of things. We found two main things in this paper: that you didn't get more oil by drilling more, because you had to drill slowly and carefully with geological information that would accumulate over time. And the second one was that the energy cost of producing the oil was increasing. And this goes back to my looking at how much energy the fish used in migrating versus the energy they gained from the migration. And so we tried the same thing. We're looking for petroleum and found out that we went from getting 30 to 1 and occasionally 50 to 1 in a given year down to 10 to 1. It was declining regularly. So the energy return on investment, my minor or medium claim to fame in science, was declining. So, but in 2001, is there a question? I can't see anybody. If there's a question, just speak up and turn on your mic. In about 2001, I decided I needed to learn more, so I went to find this guy. This guy is the only person in the world who knows how much oil there is. His name is Jean Larrère, and here I am at his farm in central France. He's retired, beautiful place. He's very hospitable. And all of the world, the only information we can trust about how much oil there remains in the oil is in the attic of his farmhouse. And that's amazing. Almost all of the other information is wrong. And it's politically wrong because people don't want to face the end of the oil age. And the basic problem is this. The black line, this is from 1930 to 2030. And the black line is how much oil we've extracted or produced. I mean, nature produces it, but we say produce it when we bring it above the surface of the earth. And the vertical bars are how much we discover. And you see, back in 1960s, we discovered a lot more oil than we used. We discover 3 or 4 times more oil than we used. But we found less and less and less over time, and this trend has continued till today. I can even less than that. And we're using now more than we have, than we find each year. So if you think about it, if I know that at least one of you is statistically oriented, the integral of the area above the black line going up to the bars, the integral of this area cannot be greater than the integral of this area. In other words, the oil we found back in 1970 and before, we're burning now. So sooner or later, we have to run out of oil. This is including fracking. Sooner or later, we have to be running out of oil. So from what I learned from Jean Larrière, is the data, especially the official data, is very unreliable and very often politically motivated. For the official estimates of oil reserves that you might find being promoted by the United States and so forth, for the world, it comes from either BP or from the Oil and Gas Journal, and they don't do the studies themselves. They ask the countries, all oil producing countries, for their own estimates of reserves. And they can say anything they want, and that's what they publish. And if you discover an oil field in 1970, but make a addition or revision to that oil field, which are normally upward, in the year 2000, they'll add it in the year 2000, which makes it look like we're finding more and more oil, but we're not. We're just giving revisions and additions to the original oil strike. And they don't like to report, the oil companies don't like to report how much oil they have because they get taxed on it. And about half of the oil in the world comes from very large fields, and sometimes they suddenly crash. Here's an example. The second largest oil field in the world was in Mexico, and it was called Cantarell, named after the fisherman who discovered it. And you can see that they tried to push the field, they tried to increase the production by pushing in nitrogen, which makes the oil slipperier. And they did that, but they ruined the field. And Mexico is very much paying the penalty now. Now, we use a technique called Hubbard linearization. It's a mathematical technique, and the important thing about it is it gives you, if going through a Hubbard curve, it allows you from relatively early in the Hubbard curve to be able to predict the total amount of oil you will ever get from that field. And most of you won't care very much about it, but we have used this technique for all of the oil fields of the world and all the nations of the world to predict how much oil would be left. And where this is a cumulative, this is the cumulative production on the y-axis, and the annual production over cumulative production on the x-axis. And you see this allows you to extrapolate to the total amount of oil you ever will get. And there's not many oil wells that have gone to total completion, but this is for Pennsylvania anthracite. That's a reserve in the United States that we've completely depleted. But the official estimates of oil, this is the official estimates from BP or from Energy Information Agency, the Oil and Gas Journal, the World Oil Prediction. All of these are going up, 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 up. That is because they add the additions and extensions to the year in which the extensions were made, not to the year in which the initial oil field was found. Now, I realize that's pretty complicated, and I haven't explained it very well. That's not important. What's important is that that's myself, Jean Larrière, and another fellow, Roger Bentley. So we we compared all of the different methods, and we find that there is, as I showed you earlier, we're finding much less oil than we're producing. That's what this graph is showing. The brown is what we're producing, and the green is what we're discovering. And we're discovering much less than we're using, and that trend has continued. And our prediction of how much, the official estimates I showed you before are the brown lines of how much oil is in the world. And you see people say, oh, no problem. We're finding more and more oil every year. The reserves are increasing, the brown line. And we say, no, the accurate estimates are the green line. And the point of this is working with two of the best oil people in the world and myself, our estimates of how much oil is left in the world is much less, i.e., the green line, which continues to go down, by the way, and not the brown line. So we've got to deal with this. And this is using Hubbard linearization. When we publish this for all of the different types of oil, and again, this is including including or not including fracked and so forth. And if you're interested in this, I will talk to you in detail, but I'm just running through it now. And the little blip with the blue is COVID. COVID reduced demand for oil and production, and it took a lot of people out of the workforce. So our estimate of how much oil left in the world is that lower purple line, and we've updated that. I should probably put in the most recent data, and it's following the same downward trend. So this is a Hubbard curve, including our predictions. Now, this is just for conventional oil. The blue line, so the purple line is conventional oil, the stuff the only kind we had until 2008. The blue line is including in the fracked oil, and this is for the world. And the green line includes the extra heavy, that is what they have in Canada, in Venezuela, if we get it. And the red is very interesting, is natural gas liquids. In other words, between the green and the red is how much quote unquote oil we get from natural gas. If you take natural gas out of the ground and let it reach atmospheric pressure, then the heavier fractions, propane, butane, pentane, hexane, heptane, and octane, the best will come out, and we can use that to make gasoline. Sometimes. Long story. Let's not worry about that's other people's estimates are not too different from ours. Where is the remaining oil? Well, this is where the rest of the oil is. United States might be a little bit bigger there than that because it doesn't include the fracked oil, and Canada might be a little bit bigger because it's got some very, very heavy oil. It's pretty close to tar. But it gives you an idea that look at all of the to-do about Iran and Straits of Hormuz and so forth today, and you can see that Iran is a very big player. Yes, Rich, do you have a question for me?
Yeah, Charles, you've pointed out that in the United States we're getting maybe most of our oil from fracking. What
Yeah.
about the rest of the world? Are the oil
Very
deposits?
little. We happen to have good rock. I'm going to talk about that.
Okay,
We happen to have rocks that are appropriate for that because of our ancient geology.
okay.
And it's been a little bit of fracked oil has been produced in Argentina, but in a very little bit from the Baltic countries, but not hardly any.
I, I,
And
I would
and
have guessed.
also, I suppose we have the technology,
Hey,
but other people have bought it. Is there another question?
I was just going to follow up with, I thought that perhaps Russia has very similar geology and could be extracting fracked oil. Don't know whether it is.
Well, I have inquired into it, and the answer is so far no.
Okay.
Now, possibly a better answer would be they have no reason to because they have so much conventional oil. And it's much cheaper to produce. But the answer is we don't know. And that's a damn good question, I'd like to say.
So Charles, to interpret this map, is it the size of the country that indicates how big their oil?
Oil reserves are.
Okay, thanks.
Yeah. And I say this is conventional oil. So you might see why Iran is in the news, or the Gulf in general. That's where the oil is. Now, we've talked about peak oil. Now, this shows peak oil for regions in all of the basic continents of the world have experienced some kind of peak oil, except the Middle East. So here's Asia, Mexico, they're not quite continents. Europe, you see, has had peak oil. The width of the line, Europe was reached a peak around 2000 and is now down to about half of that. That's mostly England and or UK and Norway. And South and Central America has peaked. Africa, you see, is peaked back here. All of these have peaked, and this is adding them. This is accumulating them, adding them up. And the blue is U.S. conventional, which peaked in 1970, and Canada conventional, and then you have Russia is reached has it reached a peak apparently in 2019. Saudi Arabia has not peaked, and these are basically adding. Middle East is they're simply adding on top, and they're more or less flat. But the world as a whole has peaked in for 6 of 8 continents and 38 of 46 producers. We've analyzed this country by country, and 38 of 46 producers, individual countries, have followed a Hubbert curve and have had peak oil. Well, here are some. Here's United States convention. Now, we made these predictions back in 2004. That's the horizontal line. Now, this is 4 countries: United States, Vietnam, Venezuela, Yemen. They're just various countries. We've done them for 46 different countries, and they're pretty much the same. And what you see for most countries is the red dots are the empirical prediction. I'm sorry, not prediction, but the empirical values. And the various blue colors and purple are our predictions that we made back in 2004. And you see, most countries have peaked. Yemen, let's look at Yemen, has gone up and reached a peak about where our purple line predicted. Now, we had 3 different estimates for oil in Yemen: the purple, the blue, and the blue-green. And that's low, medium, and high estimates on how much oil might be remaining. And almost all of the countries followed a Hubbert curve following the low or occasionally medium oil prediction. So we know that those who were predicting honestly restricted amounts of oil back in the year 2000 were right. And those who were predicting a lot of oil have been shown wrong. Now, here's an interesting graph. You hear our president say drill, 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 but this is the total drilling we did in the United States from 1950 to 2007, I think. And this is the production, peaking in 1970. And you see all this drilling we didn't increase the oil production. What you need good geological information, not just a lot of feet drilled. Now let's go back to my PhD work. Looking at the fish in New Hope Creek back here, I came up with this idea of energy return on investment for an activity, which is EROI, energy return on investment, is energy delivered to society or to a species or to whatever, an organism, over energy put into that activity, into the energy gathering activity. And it's usually considered energy invested from society. And so we publish this in Science. It's the best place to publish at the time. And here's our basic graph indicating that, and we were too pessimistic in this, and I'll tell you why if you ask me. But we were predicting that at some point it was going to take as much energy to drill a foot as you gain from that foot. And that was on the front page of the Wall Street Journal. My brother-in-law said, "Whoa, you're on the front page of the Wall Street Journal." I mean, he's normally kind of put me down a little bit because I was a poor ecologist. He says, "How much do they pay you at Cornell University?" And I said, "Oh, about $12,000. He said, $12,000 a month. That's pretty good." I said, "No, $12,000 a year." So whatever respect he got from me being on the front page of the Wall Street Journal, I think I lost most of it there. Anyway, the best first principle: humans use high quality, low cost resources first before low quality, high cost resources. A best to worst ordering of resource exploitation. And we've exploited the best oil. We know where it is. We've exploited it. It has the highest energy return on investment, and we have to deal as best we can with what's left. It's just a look at the size of oil fields found in the United States, which way back dropped way, way down. We go after much smaller oil fields using the same amount of energy, more or less, to drill an oil well. And now, to get oil, about 10% of our oil comes from the Gulf of Mexico, from these incredibly expensive things. Now, let's just give you an example we did for Norway. Norway is the largest producer of oil in Europe ever. And this is all of the hydrocarbons they get from an oil field. Oil is the bottom, then blue is gas, condensate. That's natural gas liquid. Sorry, that's condensate. That's a little different. And natural gas liquids are essentially the same thing for Norway. And this is the cost. You see, the cost is going up and up and up during the same time period. So the energy return on investment is the orange, goes through a peak, sort of like a Hubbard peak, for oil alone, or if you add in all the gas and the other stuff over time. So, and that has continued to go down. Trump says to King Charles that he want to increase drilling in the North Sea, but this is where they are. Extrapolate that out to 2024. The energy cost of drilling finding another oil field in the North Sea is approaching an energy, a unit required for this. Now, I got a lot of attention for all of this, and I'll just show you one example. Here's the Houses of Parliament, and in 2012, that's me being introduced to speak at the House of Parliament, looking a little smug, I'm afraid. And so here I am, and they had a special panel of England's best oil analysts in there um, to cover my talk and to give uh, the okay or not to the Parliament subcommittee that was dealing with me. And they got Chris Zabrowski in the middle. That guy's really a good oil man. And here's for the United Kingdom. And we did the same thing. We made a prediction in 2002 for the future of British oil, which was with low amounts is the purple, medium amounts is the blue, and the green amounts uh, is the high estimate of how much oil they might have. And in fact, the production of oil in England continued to follow and continues to this day to follow the purple line. So we were good predictors of oil production. In some of their most important oil fields, this is the production and the Hubbard linearization, our estimate of how much, and we predicted that they make around 370 by the time the oil field closed, and it only went to 320. We were a little bit optimistic in that. Here's another one. We were a little bit pessimistic, though you don't always hit it right on the head, but we're pretty damn good predictors. And what happens is that the early oil fields were big. See this gray one down in the lower right-hand corner. I don't remember, Ecofisk or something, or Brent in the 40s, and they were the big fields, and they're still producing a little bit of oil, but not much. And now England is producing a very, but only about 10% of, or 10 to 20% of the oil that they did in the year 2000. So England had a little last gasp, and now they're suffering economically, consequently. And the I don't know what this curve means, quite frankly. Energy return on investment for UK gas at the time I presented in Parliament had declined by about half. Yes, Rich.
Yeah, I was in Norway 10 or 12 years ago, and the comment was made to me that when they discovered a lot of oil in the North Sea, they drew a line between Norwegian ownership and English ownership, and England went ahead and extracted oil as fast as they could, and
Yep.
Norway uh, did a lower rate of oil extraction, and
Right.
they have more reserves than England. Is that right?
Absolutely. In spades. Absolutely. Of course, there's a lot fewer Norwegians than English.
Yeah.
So per capita, I don't know what they did. That would be an interesting question.
Yeah. Okay.
It's the same thing, the decline of EROI for UK fossil fuels. And this is the EROI for oil for various countries. The purple is, what is the purple? I think the purple is, I don't know, Mexico, I think. It's funny, I don't have it on here. I better look it up. I can't. And the U.S. oil and gas, by two different estimates. Cleveland did it independently, and we did it in 86. So that's these middle values here. This is for the U.S. And you see, when we drilled really hard in 1980, it decreased the EROI. Didn't increase the oil produced, but it decreased the EROI. And here's a different estimate I did with Gagnon for global oil and gas. I guess this is global. I don't know which the purple is, quite frankly. I don't know. I can look it up, but now this is Stephen Moore and all a different group of people said, well, let's look at all fossil fuels, all possible fossil fuels. Blue is the oil, the red is gas, green is coal, essentially. And this is taking the lowest estimate. Note that peaks at 500. This is a medium estimate of all the estimates in the world, and that peaks at 600. And this is the highest estimate of everything we can find, of all the fossil fuel we can find. And this one peaks about now. This one peaks about 2035 or so, with oil peaking by now, which it has. And this is oil is about the same, but there's a lot more coal in this estimate here. But, you know, there's only a few more generations of any fossil fuel at all. So 150 years maximum. So that's even using the largest estimates of anybody in the world. So depletion is reality. It's occurring all the time. Nobody talks about it. And this is also depletion of grades of metals. So as we mine up the best copper, we use lower and lower grades. In Montana, we used to mine ore that was 40% copper, and now it's 0.4%. And so forth and so on. Same for lead, nickel, and everything. Depletion is a physical reality that we need to deal with. This circle in the distance here, in all of this area, I just want to make a comment about the environmental impact. This used to be all very productive marshlands, and it's now water because it's all been dug out looking for oil in southern Louisiana. There's a dredge right there, a big ship or medium-sized ship, and that's a channel going out to the Gulf of Mexico. But all of this area here has been dredged out to float in barges to produce oil and gas, mostly in the 1940s. So there's a lot of environmental impacts to all of this that I'm skipping over, but are important. And EROI will strongly influence the net economic growth, the cost of government, i.e. school bus fuel, for example, ability to pay back international debts, and ability of conventional economic models to work, which we will talk about next week. Now, just a brief bit on the limits to growth. This was a book published in 1972 by, these are students of Jay Forrester, Donella Meadows, Dennis Meadows, Jorgen Randers, and William Behrens. I know Dennis pretty well. And here they are. And it's called Club of Rome. It's called Club of Rome because it was funded by a group of industrialists from Rome to do a larger study, which they did. And they basically made the very early, very first computer model. They didn't have fancy graphing techniques in 1970 when they're doing the work. So they do it with a printer. You see, that's printer on, remember the great big reams of paper we used to use. And they looked at from 1900 to 2100, the resources. It was just very broad concepts of resources, the human population, industrial output per capita, the pollution, and the food per capita. And they did a great deal of what's called sensitivity analysis. They changed their assumptions and saw how it influenced the model. And it basically didn't matter very much what assumptions they made on how big the resources were or how fast the population grew or whatever, that sooner or later this the population would decline. The food per capita would decline. The pollution would increase and the population would decline. And this, this caused, this was the biggest environmental discussion that the world has had. The economists hated it, mostly because they thought human imagination or technology or market incentives would overcome any important constraint of nature. And as an example of where they are right, I tell you that George Mitchell and fracking supports their viewpoint. The trouble is that basically we've gone through the sweet spots. Fracking has had its day, and it just delayed things for a couple of decades. Well, that's pretty important because we've lived through it, but the problems still remain. And when the violent oscillations did not occur, they dismissed the model and analysis. And here's just some nasty comments by various economists from Columbia and so forth. The model was highly criticized because we didn't include human innovations, which economists think are so important. And when the dramatic changes did not come to pass, they loudly proclaimed the model to be a failure, but the critics didn't understand the timing. And this is something I did with one of the original things. I just took a ruler and a variable focus Xerox machine, and I found out that these peaks in population are not supposed to have happened yet. This was the original model, and although they say food per capita should be declining by now, and I think it probably is. So anyway, various people have looked at this, and the model is still pretty much on target. These are the various predictions of the model in the dotted lines and the actual data in colored lines. And depending on assumptions you make, the model maybe is still pretty good and maybe still scary. Well, anyway, the economists say leave it to the market, and that's what still we're doing. But I say Mother Nature holds the high cards. Depletion is clearly trumping technology. The political issues are coming in now. Which is winning. New technology appears not to have found more oil, but only it extracts existing oil faster. Whoop. We're almost done here. And it has often failed. And here are some examples. Yemen tried horizontal drilling. It didn't work. Prudhoe Bay tried flooding with water and nitrogen. It didn't work. So, technology doesn't always work. And there we are right now today. The economist's argument, technology will overcome depletion. And the geologist's argument is depletion is real and will overwhelm technology. Who is right? And I say because EROI continues to decline, that it's now below 10-to-1 most places in the world, that depletion is trumping technology. So here we are today. All the news media worry about CO2 and climate change, which is a big problem. But I think there's this bigger wave that we're not looking at called depletion. And that's my point of view. And my final professional goal, since neoclassical economics is oriented towards technology always winning, that my final professional goal is to push this rock called neoclassical economics off the cliff. And that's what the rest of this course is about. I am done. Now, how do I get back? Stop share. And it is 1:04. I actually am almost on time, and I am open for discussion, and I hope you have some questions.
I wanted to ask about one of the graphs you showed of all the countries or continents. It was a very
Yeah,
colorful graph. It ended at
excuse
2020.
me, who's asking this question?
This is Elaine. I'll turn my video on.
Yeah, if you don't mind, it's nice
Yeah,
to
no,
see
it's
you.
fine. Your graph ended at 2021, I think, for
Yeah,
all of the countries or continents. And I wondered if you had data after that, because some of the curves were going up at the 2021. And I wondered if that was continuing or what you knew about the last 5 years.
well, I tell you what, I will write Max and see if he's updated it.
Okay, thanks.
Mark,
Um, your point
excuse
about
me, Richard, will you send? I'm not going to remember this by the time I get home. So, Richard, will you send me a email and with Elaine's address and remind me to get an update of Max, uh, Australia Max, whatever his name is, Kumaru, graph. Okay, so I'm sorry, Mark. Go ahead.
that's right. So your point about depletion beating technology in the fossil fuel realm, that I think the data is pretty convincing. Has anybody looked at renewables, especially solar and maybe fusion in the not too distant future, and whether that sort of technology shift might be the way to escape?
Uh, okay, first of all, in my daily email, I'm caught in a swarm of mostly colleagues, but sometimes adversaries, um, who are either very pro. It's amazing. I'm in the middle. Um, People are really gung ho solar or renewable, shall we call it, and people who are not. And the problem is, um, the problem with solar, if you just look at a solar unit, the ERI is pretty good, moderate, maybe akin to oil today, if except for the intermittency. And so when I first studied wind turbines in upstate New York, I take my classes out there and they say, oh, they're great, da 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 da. But the problem is that the wind wouldn't blow for 2 or 3 weeks straight in the summer. And they were useless. Now, in New York, there's a great big dam called the Roosevelt Dam on the St. Lawrence River. So if you don't let any water through when the wind's blowing and let the water through, you might have storage, but that's for 2 weeks, and you might not. But that's the problem you reach, the problem you deal with all the time. You don't have the storage, and storage, although it's getting cheaper, is very, very expensive. And so I can send you papers on that, Mark, if you want.
Yes,
Uh,
please.
I do not know of one that puts it all together, although I'm trying to collect them in a new journal section I'm doing. I'm trying to get an answer to your question. And the other person who doesn't think, it's not just one person, but it's principally Simon Michaud, who's, despite his French name, is an Australian living in Finland, um, has done a really good analysis of the materials you need and the copper you need. For example, an EV car has 3 times more copper than a combustion car, and so the copper, the materials you need and the energy cost of the materials is very, very large. So that's another problem. So we don't have answers to that. Here's an example, one that I studied or I went to a lecture about. I didn't study it much. Was in Ireland. Ireland is interesting because it's got three windy areas: the west coast, the east coast, and the south coast. And always one of them, the wind is blowing. Supposedly. So you can hook. So each of them has to be capable. If you're going to run Ireland on wind, you have to be, each of the three areas has to be capable of producing the total electricity you need, which means you need enough wires to carry all the electricity that Ireland uses from east to west to south. Not to mention I don't know if they're going to give any electricity to North Ireland. That might be politically a little bit difficult. I don't know. But so the cost of the wires alone brings the EROI of renewables for Ireland way down. Because the wires are made out of aluminum, and aluminum is a very energy intensive metal. And so basically our complaint is this: these are the kinds of studies that our nation should be doing, but we are not. We are leaving it to the market, and the market can't look ahead to a time when there's very little oil available. And in other words, if you're going to build wind turbines, first thing, the blades are made out of fiberglass, which require a huge amount of oil. And then have you seen the pictures of them transporting the blades? The energy intensity of all of this stuff is astonishing. And we won't, I've done, in my opinion, the best study yet of solar, although the data is old, with Pedro Prieto from Spain. And we found when you followed the money to look at the energy required for all the money required to build a 1 gigawatt solar collector, that our estimates of the energy costs were several times that of people who just looked at making the panels.
So make a comment. I think the most important insight of the limits to growth study was that if you're growing exponentially, if one thing doesn't get you, something else will. So if you can solve the oil problem by putting up solar panels, then you run out of cobalt for the batteries.
Copper,
you
whatever.
run out of something. And just your graph showing the overall oil production, the demand was still going up, wasn't it? It's been going up all the time. And that's the problem. That's the fundamental thing that damages the earth. And if one system doesn't get damaged, another one will. And pretty soon you run out of something.
And you've reminded me one thing I did not say about the limits to growth study. The only way they found that they could stabilize the system was to limit population growth, stabilize the population, and stop investing, except for replacing what you had. Stop new investments. Those were the only way they could make the limits to growth stabilize. A lot of people don't understand that. And if you look at the news, you look at the media, right, everything's about investments. Every politician is running on growth. We'll give you more of this or more of that. Whether left, right, center, whatever the hell they are. So we're just built into this growth thing. And thanks for reminding me of this, Max. And we're kind of just stuck there. Mary Ellen.
Well, I'm thinking that climate change and pollution are going to reduce our ability to live probably more than the lack of energy. I mean, we're
The
going to
race.
have we're going to have yes, we're going to have a big population shift, and I think that's going to be a major source of reduction of population.
Everywhere on Earth is populations are stabilizing. I think just giving women a choice, they choose not to have 8 kids, and except southern Africa, sub-Saharan Africa is still growing. Every other place, I mean, like Korea, the population is declining. Lots and lots of places that you give women a choice in, birth control technology, they don't want to have 6 or 8 kids anymore. So this seems to be happening all around the world.
We just watched a YouTube.
I'm more concerned about the immigration. I mean, people are not
Yeah.
going to be able to live in Bangladesh with the sea rise. People are not going to be able to live in New York City with the sea rise.
We
So
just
we're going to
watched
have immense
Redistribution.
migrations of people.
We just saw a
Yep.
video by Jonathan Tam at Oxford, who's I don't know if that's a Korean name or a Chinese name or Japanese, but he was talking about the birth dearth in Japan was going to cause a disaster, and their population is going to go in half by 2100, and they have to take care of all these old people. But my point of view is that that's the salvation.
I agree with you, Max.
We're way
I agree.
overpopulated, but rational.
But
There's
the
two
trouble
ways.
is that
There's two ways to end overpopulation: increase mortality or decrease fertility. And a lot of rational women are decreasing fertility, and that could go a long way toward fixing things.
well, somebody said, I guess it was probably Paul Ehrlich, that who just died incidentally. He was one of my heroes as a grad student. He said that that control will take place. Population control eventually will take place. The only question is whether it will be by procedures we like or procedures we don't like.
But population control didn't work very well for China. They should.
Oh, it did. One child, one family, one child worked very well.
But they all turned out to be boys because people got rid of the girls.
People say
Didn't
it
turn
didn't
out
work,
very
but
well for the boys who like girls.
during the 35 years of the
Boys
one-child
who like boys.
policy, China's income, per capita income, increased 20-fold, roughly.
Yeah.
So to say it didn't work, it depends on what
It
you're trying
worked
to make
very
happen.
well for improve. And I agree with you, Max. I think it would work around the world. I don't think it's a good thing for. I don't think it's a good thing for people to try to boost the birth rates. I think now how we're going to take care of old people like you and me, I don't know. But that's. I think all you got to do is make the wealthy pay their fair share of Social Security. I don't know why it should be capped.
Yeah. And the other
That's
thing
all
to
you need
notice
to
is
do
that
to
if you
fix
do
Social Security.
if you do a pro-natalist policy, you still have to wait 20 years before those kids that you stimulate to be born are going to help with the dependency ratio. They're dependent too. They make it worse for 20 years. And by then
Well,
we're
I
all
figured
gone, so the problem is solved.
this out when I was 20, and I have no children by choice.
Mhm.
And I married a woman that had 2 children from a previous marriage, and that's just fine. I like them, just get along with them just well. But Rich, you got a question?
Yeah, as we're bringing up China for population, to what extent has China been used as a model for energy peak and energy distribution between resources? Because they have an overwhelming amount of coal, very little oil. I don't know about natural gas, but I think fairly
Not
low
much.
supplies.
Some.
But they also have a high percentage of the rare earths on the in the world, And so they have a different model, I would think, of energy use. Is that
I think I think it's very interesting to watch China because unlike our current administration, which incidentally just yesterday fired all the advisory committee of the National Science Foundation. I mean, what they're doing is just I carry a poster in the marches, that says "Make America Great" by colon destroying its university, destroying its science, destroying its healthcare, destroying its alliances, and on and on. So what we're doing is enormously weakening. In the meanwhile, China, that believes very much in science, is building a lot of renewables in look like intelligent ways, and they go to the mountains in Mongolia or next to Mongolia, the high areas where there's less less atmosphere, so they get more sunlight. And they build their solar installations in way up in the mountains facing south, huge mountainsides, and then I guess they got to build long wires, but they're doing all kinds of things they're building entire universities for petroleum, in entire universities for solar, and beautiful universities. And they're just investing in science to the nth degree while we're destroying it. So now is China does not have much oil, and the energy return on investment for Chinese oil is very low. We've done an analysis for it, and it was 5 to 1, which is barely you can run a civilization on it. But you're right, they manufacture things and trade it for oil. But more than that, they're selling electric cars. I understand you can get a quite good Chinese electric car for $25K, and we have to pay twice that. So whatever they're doing, they're thinking about it very logically and very carefully. And I don't know. I've spent quite a bit of time in China and teaching it, and I found it wonderful. I really liked my students from China enormously, and they were kind and caring and very, very good students. But as one of my Chinese students, I said, "How come these Chinese students are so good?" And he says, "Well, when you get the best of a million, you're getting a pretty good product." That China would figure out who were their best, brightest students, and then oftentimes they'd encourage them to come to the U.S. in my day. And so one of my Chinese students is now an outstanding scholar at in all kinds of awards at Boston University, and another one is in their Chinese MIT and right up at the top, and advises the government, has an office in their government. So the Chinese are advising their equivalent of senators. So that's, they're being very, very smart. And I don't think we are. Okay, any other questions? Good. Melissa, yes.
Hello. I just kind of, I don't know. I was wondering, like besides gas and cars, what are like the top 3 things that oil is used for?
It's used in industry for all kinds of things. It's used for feedstocks, meaning every plastic you have was originally oil. Your shampoo, whatever, everything that's not doesn't look like wood and metal, probably plastic, is probably oil one time. The residual, I don't know if I'm doing the top 3. what's the bottom of the barrel is tar, so all of our tarred roads are from oil. Let me think. What have I missed?
Well,
Plastics.
half the world's food comes from natural gas through nitrogen
Oh,
fertilizer.
natural gas to make
And
nitrogen
another big
fertilizer.
one with
Yes,
natural gas is cement, which is a huge product the world's
cement's a
built
lot
on.
to what's called kiln cement.
Yeah.
Cement doesn't dry; it absorbs water. You drive the water out, and then you absorb the water. Let's see. If you are interested in learning more of this, there's a guy named Vaclav Smil, Smil, and he says that there are four main ingredients of society: steel, cement, ammonia, and plastics, I think he says. And essentially we built society from those materials. I mean, you don't build society from ammonia, but you build the food for the people from ammonia. And he's written several books that sort of answer your question, Melissa. But I think if I say, let me see, I think industry, home heating, we do most of that with gas. We don't produce much electricity with oil because gas is cheaper and coal is cheaper.
Transportation is huge with oil.
Transportation is huge. And diesel is probably, uh, here's what you do. You take a barrel of oil and you put a lot of energy under it. You heat it using natural gas and in a tube. And you've seen these cracking towers. And what the heat does is it cracks, it breaks the long molecules that were original biology of a ancient clam or phytoplankton or whatever, and you crack it into little pieces, and they go up the cracking tower, they go up the tower, and then the lightest ones come out up at the top. They just have pans up there to collect it, and then next lightest and light and so forth. So the top one will get things like butane, and the next one will get things like octane, which is best for gasoline. And then you'll get maybe, I guess, 20 carbon links, which is diesel, something like that. 20 carbons linked together. So the lightest natural gas is one carbon surrounded by four hydrogens. And then propane, butane, methane, no, butane, butane, pentane, hexane, heptane, octane, whatever, pentane. So, but you make these cracking towers. You've probably seen them in California or New Jersey and or Louisiana. That's where we distill our gasoline and I mean our oil, because the stuff you get out of the ground, you can hardly do anything with it. And then what's left at the bottom is called bunker, and you run ships with it, or you used to. And that would be the cheapest oil.
Thank you.
Um, that a really wonderful book. It's written by my friend Alice Friedemann, and it's called When Trucks Stop Running. And she thinks the big issue will be diesel. And she thinks the problem with electric trucks is that they're going to spend most of their energy carrying around their batteries. Now, some people argue this. I don't know. But diesel, I mean, all you got to do is look at Route 5 and look at all the trucks. We just spent a day looking at them, and there's a lot of them. And they're just moving everything we eat. And I drive around Ashland, and I think, if we did, if we were ate what we produce locally, all we'd eat is pears. Just and drink wine. There's hardly anything we eat that's produced anywhere near Ashland.
I don't think that's necessarily true. There are a lot of farms growing a lot of stuff, and there's farmers markets and the co-ops that are selling that stuff. So
Twice the price. It's
My
You didn't
twice the
talk
industrial,
about
price.
price. You just said availability.
Yeah, that's
my
true.
industrial
But
farmer
I did a
friends,
study. I did a study in Syracuse. It had a great farmers market that we spent a lot of time there, and that was cheap. But I did a energy cost and found that it was actually cost more energy because a pickup, a quarter full, driving 30 miles, used far more gasoline per pound of food than a semi coming from Ohio, where the food grew much at a much higher EROI. How's that? A lot of greenies don't like to hear that, but a big truck going at 8 miles per gallon delivers a hell of a lot of pounds.
Are you considering externalities, the pollution that puts in the air?
Well, the pollutant's less because then the pickup coming from 30 miles away, a quarter full, because it's carrying so much more. You need to carry that same amount of food, you need 200 pickups. And how much pollution do they make? Of course, we'd rather pollute Ohio than New York, but
agriculture uses a lot of diesel. My farmer friends tell me they use 100 gallons of diesel a day when they're spreading their manure with big
we
machines.
drove across the country
Unbelievable.
about 8 years ago. And to me, it was so depressing because the entire middle of the country, from the edge of Montana going, I don't know where, Wyoming or into Nebraska, all the way until we hit Kentucky, was horizon to horizon. This was March, dirt, plowed dirt, uh, and not even cover crop, getting ready for corn. And at one end of town, there was petrol stations, diesel, gas, gasoline, whatever. The other end of town was distilleries for the corn.
Great.
And I've done a study that shows that you just get about 1 joule of energy or 1 calorie of energy for every calorie you spend making the fertilizer, running the tractors, doing the distillery, and not a stick for a bird to sit on or hide under. And I just saw something marvelous. You should go on NPR and look at this presentation, 1 hour, called Wilding. It's the most wonderful show I've seen in a long time. Wilding. If you don't have Compass or you don't have access to NPR, it's the only good stuff on TV, basically. And the article, I'd really like everybody to watch that article. It was great. Okay, any final questions? Everybody happy? It worked. It worked. The whole thing worked. I can go camping, and yeah, I'll show you if you haven't seen it. Here's a view out my window. Can you see it? There's Columbia River Gorge. I don't know if you still can see it.
Yep.
Could you see it, Donna?
Yes.
Yeah.
Yes,
Okay.
I can see it.
And here's my little camper.
Looks pretty big.
No, it isn't. It's the smallest there is, almost.
Sweet.
It's a base camp. I shouldn't say it's our. My wife is off hiking. And just a minute, I can't get back to. Dave. I'm trying to get back so I can say goodbye.
Just say goodbye. I gotta go.
You're visible.
No, hang on. I insist.
Yeah, we can
Okay.
hear you. We can hear you, Charles.
Okay, and my dog found a mouse in the trailer last night in the middle of the night. It was
Oh
just
my God.
crazy. Okay,
Thanks a lot.
won't see you Thursday, Donna.
Okay, bye.
Bye-bye.
Thank you. Bye.
Thank
Thank you,
you.
Richard, for helping me.
Thank
Richard
you.
helped me make
Thank
sure
you,
there was a
Richard.
backup and
Thank
everything.
you.